All right, let's take a look at review problem 4.11. We have a number of Bernoulli trials that are done. S sub n is the number of successes in n trials, and there's a probability of success of p on each trial. Problem number 1 goes like this. Suppose that I have these trials, and I know the number of successes in the first n trials. Then what is the expected number of successes in the first m trials, where nm is less than n? Okay, so to do this, let's figure out the various distributions here. So let me define a few letters here. So S sub m will be the number of successes in the first n trials. S sub n will be the number of successes in all n trials. And let's let capital R, and let me give this a letter, n minus m, will be the number of successes in these n minus m trials. So in S sub m is number of successes in first m trials. R sub n minus m will be number of successes in trials m plus 1 through n, and S sub n will be the total number of successes in the first n trials. And so clearly, the way that I've rigged this, S sub m plus R sub n minus m is equal to S sub n. Okay, so to do number 1 here, let's find the conditional distribution for S sub m. So let's find the probability that S sub m is equal to I, given that S sub n is equal to j. So let's figure out the conditional distribution of S sub n given S sub n. So by my definition for a conditional probability, this is the probability that S sub m is equal to I and S sub n is equal to j, divided by the probability that S sub n is equal to j. Now I'd like to split this up, so the way that I'll split this up is I'll write this as S sub m is equal to I, and the remaining number of successes is j minus I, divided by the probability that S sub n is equal to j. Now these two are independent, and so I can split probability that S sub m is equal to I times the probability that the remainder is equal to j minus I, divided by the probability that S sub n is equal to j. Okay, now everything here is binomial. The only thing that changes is the number of trials. So if I want m trials and I want I successes, the chance of that happening is m choose I times p to the I times 1 minus p to the m minus I. Now for this next one, I have n minus m trials, and I want j minus I successes. So that'll be p to the j minus I times 1 minus p to the n minus m minus j minus I. Then I divide by, here I have n successes, and I want n trials, I want j successes. So p to the j, 1 minus p to the n minus j. Okay, now let's simplify this. First off, p to the I times p to the j minus I is p to the j, and that cancels the p to the j in the bottom. Over here, I have m minus I. Here I have negative m plus I. So the net effect is I have 1 minus p to the n minus j, and that cancels out the 1 minus p to the n minus j in the bottom. And so what's left is going to be m choose I, n minus m choose j minus I, over n choose j. And I recognize this as something that is hypergeometric. So the conditional distribution of S sub m, given that S sub n equals j, is hypergeometric. Now the parameters are, here the number of trials is little n, the good ones are capital M, and I'm looking to get I successes here. So actually the number of draws is equal to j. So So the total number of objects is little n, the number of good objects is m, and the number of times that I draw is the j here. So therefore, by using properties of the hypergeometric distribution, the expected value of S sub m, given that S sub n equals j, will be equal to the number of draws times the number of good objects over the number of total objects. And then eliminating the j variable, that means that the expected value of S sub m, given that S sub n, will be equal to m over n, not times j, but times S sub n. Now, does this formula make sense? M over n times S sub n. What the formula says is that if I know the total number of successes here, I expect the number of successes in this part to be simply m over n times the number that I've already received. So the formula makes sense. Let's now take a look at problem number 2. And actually problem number 2 is significantly easier than problem number 1. This time I have n successes, or n trials, and I have an additional number of trials over here. So here's m trials here, and so there are m minus n trials extra. So once again, S sub n is the number of successes in the first n trials. Let S sub m be the number of successes in the first m trials. And in this problem, m is greater than n, so the remaining number here, r sub n, will be the number of successes in trials n plus 1, n plus 2 through m. So the problem asks for the expected value of S sub m given S sub n. Okay, well, let's see. That'll be equal to the expected value of S sub n plus the remainder number here, r sub m minus n, given S sub n. Okay, let's split this up. The expected value of S sub n given S sub n plus the expected value of r sub m minus n given S sub n. Okay, this one's silly. If you know S sub n, then the expected value of S sub n is S sub n. That's silly. This one, the number of successes here is independent of the number of successes over here, and so that'll just be the expected value of r sub m minus n. So finally, S sub n plus the expected value of this binomial random variable, which is the number of trials times the probability of success. Now, does this make sense? If I know the number of successes here, then the number of successes in this bigger part will be the number of successes that I've already had plus the number that I expect to have in the future. So the formula makes sense when I think about it in terms of English.